All right. Welcome to the very last day of our winter school on data economics. I'm delighted that we've got Rachel Cummings here, coming from Columbia University in IEOR. Rachel's PhD is from Caltech a number of years ago, and she's one of the main people thinking about introducing ideas of privacy into markets and thinking about how preferences for privacy and behavior affects outcomes in markets and the interplay of that between adoption of privacy or not. So it's great to have Rachel presenting this stuff today.
Thank you, Jason. Thank you, Rita, for the invitation. This is, not enough time in Morocco. Invite me again. I'll come back. It's been amazing. Thank you, everyone, for being here. I know this is our last day, and so hopefully you still have some strength in you. Okay, so we're going to be talking about privacy. And it might seem like this is kind of unrelated to everything we have been talking about this week of predictions and markets and pricing and now privacy, kind of random. And what we're gonna do today is I'm gonna spend the first part before the break, not even talking about markets, economics whatsoever at all. And then in the second part, I'm tie these all in and we'll see how does the way in which we formalize privacy impact things like truthfulness in games, utility, costs in markets, and so on. So hopefully by the end I will convince you these things in fact are very much tied and very much related, but you won't probably see that until after the break. So I sent out the notes, and they are much more detailed than what I'm going to do on the board in our limited time. Otherwise, I would get through half of one document. But they are a very detailed, and so if you are interested in this and you want to read more, the notes will have more specifics and additional references. Okay, so we're going to start with the definition of differential privacy, because this is a differential privacy in markets. I feel I have to start with a disclaimer. There are lots of ways of formalizing privacy, and this is just one. And we'll see in part 2 why this is a formalization of privacy that sort of plays well with all of our economics things that we like. But it's important that I include the adjective differential privacy rather than just privacy, because there are lots of other flavors. Amazing timing, everyone. I was just waxing poetic for a few minutes until you got here. Okay, so let's start with differential privacy. First of all, who here has heard of differential privacy as a concept? Okay, good. That's more than I thought. Who has more than heard of it in passing? More than I thought. Amazing. Okay, great. Huh? More than in passing. More than yes, I've heard of that word, but who's yes, I think I know something about it. But that was more hands than I expected. So this is great. I was assuming no one heard of it really. So good. Okay. So as a property of an algorithm, so we'll say that an algorithm M, and in fact in privacy land, normally we call these things mechanisms, which is very confusing if you're coming from a mechanism design background, because it is not a economic mechanism. For some historical reason that I don't fully understand, the field just calls a differentially private algorithms mechanisms, but it just means algorithms. But I use M for them for that reason. Okay. So an algorithm M, the maps from some set of data into some arbitrary output range R. And so this is I I have data coming from n people. And as foreshadowing, this might be bids or type reports, but it might also just be like, you know, your like heart rate data. Is epsilon delta differentially private if for all possible neighboring databases, let me write bigger, by which I mean they're the same except for one person's data. So we'll say like X and XY in our database space. And for all possible subsets of things in my output range, meaning like for all possible things I may produce, I want the following to hold. I want the probability that if I run M on X, of it falling in some range, to be close in a parameterized way to the same probability if I were to run M on Y. How's my font size? Can you see in the back? Yeah, okay. Okay, so let's like pause and interpret this for a minute. So we are like protecting neighboring databases, meaning I'm saying if I change one person's data, for example, your data, I want to make sure that I produce about the same thing. So you can think of this as like if I like choose to like participate in the analysis or not, or if I'm truthful, or if I lie, whatever is my action, we're going to get out about the same output. How do we formalize this? So we're saying for all possible things I may produce, I want to produce that thing with about the same probability. And this closeness is measured in both a multiplicative and in an additive sense. And the epsilon is our main parameter. So let's like ignore the like a delta for a second. So I'm saying I want the ratio of the probability under X and under Y to be close up to this like multiplicative factor. So we oftentimes will draw pictures like this where we say like, you know, here is a PDF of the output under X, and like here is a PDF of the output under Y, and they're close. And like how is this privacy? So we're saying for all possible things I may produce, I want a bound on these ratios. So this means from a privacy perspective, imagine if an adversary observed S as the output, right? They like observe posted prices. They observe results of some like medical study. And they try to guess, was it because your data was yes or your data was no? And this guarantees information theoretically that they cannot make a strong inference about the content of your data besides like the amount allowed by this ratio. So now what is our delta parameter? I'll first say it's like why is it in the exponent instead of a like actual factor? There's no real like a philosophical reason. It just sort of is. I think like historically, this was introduced coming out of the like a crypto community, and they're used to thinking of things that are like exponentially small, and so it just appears here. It turns out it'll make some of our math a little nicer later down the road, but that's not a real reason. That's sort of more of an artifact, and so there's no like deep thing if you're wondering why. So now let's think about our delta term. Let me actually make these a little bit multiplicatively closer. Okay, so go, why is our delta term nice? So for one thing, it might be this value could be 0. So it could be that like, this is 0 and this is something very, very small. But still, it's like even in this case, if this is 0, if I don't have a delta, there's no epsilon for which this can be dp. And so the delta allows you a like very small additive slack in some place if you want to like have a little blip somewhere. Visually, it allows you that. This can be helpful also if, let me see, how many zeros did I put here? I put 5, so let me put 6 here. And so we're saying these are not like a multiplicatively close because they have like a couple extra zeros here. And so if I didn't have a delta, it's possible this can be like an epsilon dp, but the epsilon would have to be really big to make this possible. And so if I allow a little bit of a delta, it's like, no, we're like, talking about like a low probability events here. A couple notes on what are like quote unquote reasonable ranges of these parameters. So for epsilon, first of all, there is no consensus, and this is a like hotly contested question and an active research area of like what is a good epsilon. Theorists will tell you, maybe like 1 over square root n is a good thing, or some small constant is a good thing. And like, this is a good value of epsilon. Practitioners will tell you, I can't work with that. And we'll see why. Inherently, there's a like privacy accuracy trade-off, and we'll see it. And then like practitioners will tell you, these epsilon values are so small that my accuracy is bad, and I need to like position myself somewhere else on the curve. And so they go for like, 1, 2, 4, 10. And there's sort of a consensus where if you like, use something in this range, no one will get mad at you in your ICML reviews. But that's like not a real reason of like, why it's good. This is sort of, as it's an open question, people will not be upset at you if you use numbers in this range, but that's not saying it's good. But so like it's like you should think of this epsilon as a small constant, but not like exceptionally small. The delta, on the other hand, there's sort of a consensus. The delta should be really small. There's sort of a disagreement here again. Theorists say maybe it should be like exponentially small in the size of our database. In practice, it looks like 10 to the minus 5, 10 to the minus 6, something like this. But there's a consensus it should be a really small number. And that's because a delta can be thought of as a failure probability of your privacy guarantee. And you really, really want that to be small, especially because your delta is a bound on a probability. If it's like half, even this is like catastrophic. If it's 0.1, catastrophic because it's like 10% of the time absolute failure. So you want it to be really small. Any questions? Yeah, please.
What do you mean by neighboring data set?
Good. So this neighboring means same except for one person's data. Differ in, I'll say, your data. That's what this means. So we're saying, so we're really comparing what can I learn on the world with you and what can I learn on the world without you. And if I'm learning the same thing in both cases, I'm really not learning about your data. I'm not leaking information about your data. I'm learning from the population. I'm learning there's a causal link between smoking and lung cancer, but I'm not learning about like your personal health information.
Also, the epsilon and delta,
Mm-hmm.
in order to make this as a probability measure, they cannot be independently chosen, right?
These are not probability measures. Oh, thank you.
Okay.
No. Or you mean the like probability
Yeah, so
of the mechanism?
To one, right?
They do not. Yeah. So the thing that has to aggregate to one is the an integral of this over all possible things in the output space. Yeah.
The mechanism is random.
Huh?
The mechanism, you're taking probabilities. What is random there? The mechanism?
Mechanism, yes. Yeah. Actually, that's extremely important. A randomized algorithm. Sorry, it's very small, but this is an important word. One of the questions on your problem set will be figuring out why is it important that it is random and what breaks. If it's not, but it is in fact absolutely critical that it's randomized, and if it's not randomized, then you can't achieve this.
So you mean that the values of x are random variables on R, probability on R?
So this is a randomized algorithm that maps from a database into some output.
So the output, so the solution, I can view it like a function from x to the power n to probabilities over R.
So this doesn't have to be binary, but yes. And this can be like an infinite size.
To have randomization, it can be I select x at random and deterministically I choose R, or x to the power n is.
So this is a database. So I take in a database of, let's say, everybody's medical information, and I'm going to publish something about it, my output range. And I'm going to have a randomized function mapping from the received data that can be arbitrary to the output. And importantly, let's sort of interpret what this definition is saying in terms of these for all quantifiers. Is it is worst case over all possible databases. So it's not enough if I say on most databases it's fine, and with high probability over databases it's fine, because maybe you're in that database and your data gets leaked and you file a lawsuit. This is not okay. And so we have to say, for all possible data that might be observed, for all possible realizations, you're still going to receive the same like a privacy guarantee. And then we also have, in terms of outputs, think of this S as the collection of bad things that might happen to you as a result of your data. Anything you are worried about might happen tomorrow, 10 years from now, if somebody were to see all of your secret information. I'm promising no matter what collection of things you are worried about, you are receiving privacy with respect to those collection of things. So it's for all possible data that might exist in the world, and for all possible things you might be worried about, I promise you that if I change your data, that bad thing is going to be no more likely, aside from the amount allowed by the epsilon and the delta, than if I had never seen your data at all. So in that way, it's a very strong privacy guarantee. Yeah.
These events might not be measurable, right? As in,
Yep. Don't even have to be. Can be measure zero events, but measure zero events still happen, and you were receiving a guarantee even against those things.
So there is a difference.
no, like the definition of the probability
This
randomized
S.
algorithm in S. If S is not measurable, the probability might not be
I
well
think
measured.
R and S are finite, if I'm not wrong. They are not
No, they can be infinite.
Ah.
Yeah. Let's hold off on questions about this, because we're going to see some specific algorithms that will satisfy this. Bless you. There will be sort of well-defined and well-structured.
Because if you do a probability on S, it should be at least measurable with respect to.
So let's hold off on questions of measurability. In fact, I will not talk about measurability. Okay. Okay. Okay, well, I'm from computer science, so we're going to see some algorithms. Talk about it at the coffee break. Okay. One sort of minor comment that is worth making notation-wise is that you can formalize data in this case, as you can say, well, my mechanism maps from some data space with n people into a range, which is like saying my data takes the form of a matrix, and I have n people, and for each row is one person's data, so I have like Alice and Bob, and 0, 1, etc. And then like a one person's data is one row in this matrix. And then I'm saying if I were to change one person's data, it means I change Bob from being a 0 or from being a 1 to being a 0. And these are my neighboring databases. I can alternatively say that my mechanism maps from a vector of counts. I know here I know all the mathematicians are I'm gonna do things in like infinite dimensions. From a vector of counts to my output range, by which I'm saying that my data takes form of a matrix where I'm basically counting how many people have like a data type 1, how many have type 2, and so on. Which of these makes more sense depends on the size of your output range and on the sparsity of your data. So like, for example, if my database is like, 0, 0, 1, 0, well, then I can store this as just, I have three zeros and 1, 1, and these are equivalent. If my data universe is something extremely large, maybe I don't want to write down a matrix of that size. And so like, if this is like very long and my data universe is small, this makes sense. If my data universe is sort of large or is infinite size, this makes sense. I say this because we're going to sort of like move in between them, in between these two versions. Yeah.
This question comes from here.
Yeah.
When I start doing this, so what I'm trying to say is this gives me the impression that this differential privacy will allow you to like permutate the order of the rows, and this should stick to privacy.
Yeah, good. And in fact, there's nothing special in the way this is written that I have like an X on the left and Y on the right, because it's like for all pairs. And so this must hold also if I have Y on the right and I have X on the left.
What I'm trying to say though is like, I was thinking that potentially if the last data, like the last row in my like first representation of data, it's 0, this potentially can change a lot of like the outcome, whereas like if the first row is 0, and like if I'm able to do the change like to the count type of database, then this should not happen, right? Like this means that what I care is the number of people who did X or like did this specific action.
Yeah. So we're sort of inherently making it not relevant what is the order.
Yes.
If the order is important, you can include this as a feature. Okay. So this like, data row doesn't have to be one single value. If it's important that you're in row 3 and I treat row 3 differently, then I can include that as a column of like 1, 2, 3, and so on. Yeah. One more point I want to make that will become important as a minor detail, or like isn't important, but we might have some questions if I don't say why isn't important. Is this notion of like a neighboring? In fact, there's a reason that I was a little bit hand wavy about it, is because you can actually define it in two like a different ways, and these like a different notions correspond to that. So in this case, I'm fixing that I have n people's data. And so a neighboring database, something that is like a different than one person's data, means I'm going to change Bob from having a 1 to having a 0, and I'm going to keep n people. In this version, I'm allowed also to say I'm going to like add a person or remove them. And so it might be Bob decides to like not even like participate in my mechanism. It's no longer individually rational for him, and so he leaves. And that's valid too. And so in this version, we can think about both like a versions of neighboring, of sort of like a changing one person's data, or also like I'm adding or removing a person's data. These are the same up to a factor of 2 because like a changing a person's data is equivalent to first adding and then removing. So we don't really think about this, but at some point, including in the problem set, you'll be asked to like keep track of these things, and you'll want to be specific, but don't particularly worry about that. Yeah, there's a question.
There you have several people, and then if you add or remove Bob, then again it shouldn't matter in order to have this differential privacy. But you compare the two databases, one with Bob included, and the other one with a billion of people, for example.
With what?
Billion of people inside.
Billion people?
Yeah, 100, 1 billion, whatever. So you have one database with Bob included, and then another database with, I don't know, 100 million, whatever.
With the same people as before.
But Bob.
Yes.
So unless Bob is drastically different from all the others, you won't make any difference.
Ideally, yes. Yeah.
So you need the relevance
that is the
only
goal.
If Bob is outlier. Is a so big outlier that it will change.
What if so it depends on what I'm computing. And in fact, what you're saying philosophically is true, which is why sort of a differential privacy is a nice definition that has been accepted in the machine learning space, is because if you're doing good machine learning, changing one person's data shouldn't matter. But like first of all, not everyone is doing good machine learning. And so this is a sanity check is like if it's not possible to do like a what you want differentially privately, maybe what you're doing isn't a thing you should be doing on your data in the first place. But also even in simple things, what if I say, we have a free afternoon, we can either go to the Medina or go to the sea, and we'll do a vote and we'll raise our hand, and whichever one has more, we'll do that thing. Let's say that 51% of people say the Medina, 49 say C. And then Bob walks in, he was late, and I was like, oh, Bob, what do you want? And we'll redo it. And then he votes C, and now we switch, and now we're going to the C. So it's like, so this aligns with the goals of machine learning, but people do things based on data that are not just machine learning. And in the context of sort of economics, as we'll see, if we're doing auctions, one person's bid can change everybody else's price, and then it's not so nice.
But what about changing that definition in order to compare the data set? So not you don't change just one person.
Let's talk about this at the coffee break. I have a lot more things to say. And the short answer is you want it to hold for all possible databases that you might have. I'm gonna switch the order of these two because I think sometimes seeing a concrete algorithms can be helpful, because this is a kind of abstract definition, and you might be like, okay, you wrote something down. There's some nice properties about it in terms of why this is a desirable definition and why we like designing algorithms for it. But let me tell you about the algorithms first, and then I will tell you about their properties. So first, we're going to talk about what is called the Laplace mechanism, which is a way to answer questions. So this is a way of answering real valued questions. Maybe you two can also talk at the coffee break instead of now. So this is a way of answering real valued queries. So note this, like a definition has an arbitrary output range. And I'm saying, let's just start something simple that we do with data. We compute like a real valued functions of them. So we have something that will map from my data to a real number. And I want to answer this query on my data in a way that will satisfy differential privacy. Okay, and at a high level, what it does is it first computes f, and then it adds some mean zero noise. So just to perturb things. So this is a really simple way to make sure things are randomized, and we're gonna control our noise to make this true. We have to define something first, which is what's called the sensitivity. So our goal is to hide one person's data. And so we have to ask ourselves, since I'm computing this particular function, what is the amount of noise I have to add to hide one person's data in this function? And that's exactly what this sensitivity captures. So sensitivity of some f is going to be denoted delta f, which is just a maximum over all x and xy that are neighbors of the absolute value difference of f on x and f on y. Okay, so we're just saying, if I were to change one person's data, how much can that change the value of this function in the worst case? A couple things to note is I'm still being as vague about neighbors as I was over here. And if you want to actually compute this, you have to be kind of specific if you're doing add one, remove one versus change one. And we are also taking the maximum over databases, which will ensure that we have a for all quantifier and a differential privacy guarantee. Okay, and the Laplace mechanism is actually startlingly simple. Okay, so the Laplace mechanism, and I won't even write it as an algorithm because it's just one line. So it takes in a database x, a function that I care about, and an epsilon. And it just computes f of x, and then it adds a noise term where this y is sampled from Laplace with parameter delta f over epsilon. Who has heard of Laplace noise? Wow, I'm guessing all throughout privacy. It's not a distribution that people use, aside from this. Everybody loves a Gaussian and a uniform and an exponential. This is not one of these well-loved things. It's essentially, it's a two-sided exponential with mean zero. So it looks, something like this. I can draw straight lines, and here is 0. Did I put all that? Oh yeah. So some facts about the Laplace distribution are that it has mean 0, which is good in general. If you're gonna like perturb stuff, mean zero noise is what you want. And its variance is 2 times this parameter delta f over epsilon squared. Okay, so what does this tell us? So this tells us if I want stronger privacy, then my epsilon is smaller to make this bind in a more tight way. So my epsilon is smaller, stronger privacy, which means if my epsilon is smaller, then this term will get bigger, and my variance is bigger. So if I want stronger privacy, I have to add more noise, which sort of intuitively makes sense. For my delta F term, so this captures how big of a thing do I have to hide. And if my delta F term is bigger, then my variance is bigger and I'm adding more noise. So if I have to hide something bigger, then I have to add more noise. Yeah.
The N here would be the F hidden somehow?
So the N, it depends on what.
It depends on the number of people already, so it's there somehow.
Yeah. So it's sort of hidden in your query. In fact, let's actually do a couple examples, especially thinking about delta F. So let's say that my query. Okay, so let's say that my database is just my data universe is just 0 and 1. So I'm asking how many people are over 25 years old. Okay, and so it's a yes or a no. And my function of my database is just the sum from 1 to n of these xi's. Okay, so I'm just counting how many people are above 25. In this case, what is my delta F of this function? If I were to change one person's data, how much could this change? And let's use the add remove. So if I add one person or if I remove one person, my data set, 1, yeah. Why is that?
Because xn could be 1.
Yeah. Well, yes. Yeah. It's I remove one person. In the worst case, their data is 1. Okay. So in these cases, things are nice and simple. You could also talk about fractional queries. So let's say that I have my same data universe, except now I want to ask what a fraction of people is above age 25. And now things get a little weird if we use this sort of add remove, because then I have to rescale n. So let's say it's a change one person definition. Then what's my delta F? 1 over n. And it turns out most things that we do end up looking like this, is you have a lot of counting queries, you have a lot of linear queries, you have a lot of statistical queries. And so things end up looking like this a lot of the time. They don't always, and in those cases, then in fact, a part of the research, if I give you a new function f that is not this, but is training a neural network is my function, well, then I have to do a lot more work thinking about how can the result of that function change if I change that one person data. Yeah.
What is particular about Laplace compared to other distributions?
Good. So in fact, this is exactly my next step, which, so you might wonder, why are we doing Laplace? We have lots of other other like distributions that we're familiar with, why this one?
Not because it's French.
Maybe, I'm sure that's why. There's lots of French mathematicians. Okay. Yeah, yeah. Okay, in fact, I'm going to do it over here because I'm going to prove something. Okay, so the short answer is that it's because its tails are exactly exponential. And so because we are proving things about something about exponents, that'll be important. But let me give you a formal answer. So the Laplace mechanism is epsilon 0 dp. So there's no delta, only the epsilon. As I mentioned, epsilon is like the more important parameter, and delta should just be really small. 0 is small. Okay. I think this might be the only thing that I prove in the whole thing. I have like possibly one more proof, but I might skip it if we're short on time. And although it's not a hard proof, I think that it is sort of illustrative of how differential privacy proofs go, which is a sort of helpful framework to be thinking about these kinds of things. Okay, so we want this to hold for all possible pairs of neighboring databases and for all possible things in my output. So I'm just going to fix those to be arbitrary. Okay. So fix x, y to be neighbors. Fix a function f, and let z be a real number. We're going to prove a slight modification of this definition, where instead of I'm considering all sets, we're going to consider for all r in my output range. And these are equivalent definitions if you don't have a delta. They're not the same if you have a delta. I was going to put this as a problem on the problem set, but I figured there were too many problems already. But if you solve them all really fast and you're bored, then try to prove that. That is equivalent with a delta, or it's equivalent without a delta and it's not with. Okay. Oh, and one important fact here that we will need is the PDF. Equals epsilon over delta f. Okay. And in fact, this is the real reason why I use Laplace, as we'll see. Okay, so let's try to compare, and let's say I want to bound the probability if I run it on x with a probability I run this on y, assuming they are neighbors. So I'm taking this a ratio perspective, and I'm going to show this is bounded by e to the epsilon. Okay. So this mechanism is just the function value plus some noise. So if I want to claim that my output is a certain value, it's really, that will occur exactly when this z is the difference between the value of my function and the realization. In fact, here, I know that probabilists are going to be mad because I'm going to write a probability of some a measure zero events, and we're all going to pretend it's okay. Okay, so this happens exactly when my Laplace term is exactly equal to the value of the function that I know if I fix f and x, minus this thing that I have fixed. And this is true on both the top and the bottom, but just changing y. Okay. Okay. So now I can reason about a Laplace variable, and I know it's PDF, so I'm going to plug that in. So we have epsilon over delta f. Actually, I have it written here. Times exp negative epsilon of absolute value f of x minus z over delta f. Have the same thing on the bottom. Okay, and from here is just some algebra. Let's cancel these out. I'm going to put these inside of the same exponents. In fact, I'm going to do a couple steps at once, so it's faster on the board. Huh? Yes. And then a triangle inequality. And then here's where the magic will begin to happen. Okay. Okay. Okay, so I have gotten something that looks like this, and you might think, okay, well, what do I do with this? I just have a bunch of terms and they're kind of unrelated. But anybody see it? Yeah. Yeah, exactly. Because we have bounded this exactly as our delta f. So this and then we're done. So the process goes on something like this. I compare the ratio, and I say, well, because my mechanism was pretty simple, I know exactly how to reason about the probability of this event happening. Oh, sorry, this is important. Everyone is so polite because you didn't even tell me this. Or you were confused, one of the two. Yeah, so I know exactly how to reason about this event occurring because I have a simple mechanism that is well structured, and because I have a well-behaved explicit noise, I can just plug that in, do a little bit of algebra, and then I'll see what I'm left with is a term that I have already bounded, and then things uncancel, and I'm left with an epsilon. And in fact, this is the process by which you prove a new mechanism is a differentially private. And we'll see in the properties I'll talk about shortly why we typically only think about simple mechanisms, and that's okay. Yeah. Any questions? Yeah.
About the randomization of
Yeah.
the algorithm.
Yeah.
Y is drawn once for all the data set. Y is drawn one for every x. Y is drawn every time that you ask for the Laplace mechanism. How does it work?
Good. In fact, I think I didn't put this question on the homework, did I? Okay. Okay, in fact, that was like another question I was going to put on the homework of why you have to draw it fresh every time, but I didn't because eventually it's like too many problems. But so you don't draw it for every data point, because here I'm like computing a single function that covers all of my data, and then I add one single noise term. So I like compute 40 plus some noise. If you want to run this multiple times, you have to draw fresh noise every time, and that's important for reasons that were also not on the problem set. But if you want to try to prove it, this one is a little harder, so that's why I didn't put it on there. But yeah.
Basically, take any deterministic mechanism here.
Yeah.
You add one noise.
Yeah.
And you know the parameters of the noise, and
Yeah.
you can make it the epsilon 0
Yeah.
difference.
Yeah. And so it's like, if you were doing anything to your data before, do that same thing, figure out how much noise you have to add, and then you just run it. So it's like pretty simple. Again, I feel like one of the properties of like a differential privacy mechanisms is that they strive to not make you do things that are different from your data than like you were already doing, but just some like small changes. Okay, let me tell you about the accuracy guarantees, and then I'll wax poetic a little bit more. Okay, so I'm gonna rewrite this over here so I can erase that one. Laplace is epsilon 0 dp. In terms of accuracy, we have a high probability additive accuracy guarantee, where the probability that the difference between the true value that I'm trying to get and the thing that my mechanism outputs is bounded by log 1 over beta. It's actually a log. I'll be correct this time. Log 1 over beta times delta f over epsilon. And this probability is going to be at most beta. So the question, how do you prove this? Well, you can look at this and be like, oh, this is just a tail bound of a Laplacian, and I can do some more like a PDF analysis. Looking at this term, you'll see again our friend like a delta f over epsilon appears. It's going to appear basically everywhere because this is sort of like a key parameter of sort of how big is the like thing I have to hide and how strong of a privacy protections do I want. And this also sort of intuitively makes sense because this is the like a variance of the noise, and so if I add more noise, then I should expect to have more error. And so this is what I was alluding to in this like theorist versus practice debate, because here like this is your first like a taste of sort of explicitly a privacy theorem and an accuracy theorem, and the epsilon controls both. And so if you strengthen the privacy knob, if you make your epsilon really small, well, then you're going to get higher error, and people don't like that. And like things of this nature emerge whenever you are doing a differential privacy. Is you see a smaller epsilon is going to give me worse accuracy in some very explicit way. Okay.
So Rachel,
Yeah.
you call it privacy, but you can also hear it as how can I have a mechanism such that the impact of one person is very small?
Yeah.
So
Yeah.
I aggregate, but I don't want someone to have a big impact on the decision. I don't want basically dictators or whatever.
Yeah. And so in fact, these tools have been used in things like robustness, statistical validity, generalization, because there are also cases where you say if I change a small number of my points, I don't want a different answer. Okay, let me do a race through some more facts about this. I'll just say you can do the same thing with Gaussian noise, and it will be epsilon delta dp. So that's where the delta comes in, and you can say listen, Rachel, that Laplace noise is great, but all my engineers are using Gaussians. I don't want to have to do this. Can I just use Gaussian? And the answer is yes. You'll have to have a small delta because it's a tail bounds are not exactly exponential, and so the delta comes in the tails. You can also do this in higher dimensions. And then it looks like ML takes in X and some vector of queries, say Fk, did I use K? Yeah, good. Fk and an epsilon. And let me call this thing F. So this F is a vector valued query. So I still compute F on my data, and then I add a vector y1 up to yk, where yi's are sampled iid from the same term Laplace delta F over epsilon. And now this is sort of implicitly hiding the k in here. The k is in here because now if I'm computing k functions, well then perhaps this will have a factor of k. Perhaps not if my functions are somehow well behaved and well structured. For example, if I'm asking a histogram query of how many people are 0 to 10, how many people are 11 to 20, how many are 21 to 30. Well then changing one person data cannot change all k of my values. But in general, if I'm asking k sort of arbitrary queries, then my k will appear here. Yeah.
So meaning the fx is multidimensional, is in r to the power d, k, let's say.
Yeah.
And I add to it a vector. For each component, I do this transformation, IID.
Yes.
Okay.
Yeah. Yeah. How you extend this is you make this absolute value a norm in higher dimensions, and your accuracy has a k here.
Okay.
So it all extends.
And when you say Gaussian, it means that if I replace delta Laplace delta f over epsilon by normal distribution delta f over epsilon,
Yeah.
then it will be epsilon, but there will be delta.
Yeah, it's a little uglier than just this because you also in the variance of the Gaussian you have to incorporate for the delta, and so there's a trade-off there. There's some constants. There's a square root log 1.25. It's less pretty, but it's still true in general.
You have some delta that will be added.
Yeah.
Another distribution.
Yeah. Yeah.
Conditions on epsilon for the Gaussian mechanism?
Can be anything.
Could be anything.
Yeah. Has to be positive.
Tail is different between the Laplace and the Gaussian.
Yeah. Yeah. So there's a relationship between the epsilon and delta. So if you fix one, it gives you the other because there is this inherent trade-off from the tails. Yeah. 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 And I didn't write it on the board because it's a little less pretty what the trade-off is. But in the notes, there's a site to the appendix of a textbook where they talk about this. Yeah. Mm-hmm. Yeah, good.
Yeah, there's actually a very good paper from 2 years, from 1 year ago that had multiple awards, and it's it put a framework to optimize to choose the best noise. Basically, given a problem instance, how do we calculate the best noise mechanism? And it gives something that is better than Laplace and Gaussian, but it's not non-interpretable. So one of the reasons we go with Laplace and Gaussian because it makes interpretability and proofs so many straightforward. Yes. The problem is hard enough so that we need these mechanisms that should.
Yeah. Well said, thank you. Okay, let me tell you about like a one more mechanism, and I'm not going to prove things about it, but I'll just sort of tell you, which is like this is great if you're answering real valued queries, but sometimes you are not producing a real valued output, or like sometimes like even if you are, this type of accuracy is not necessarily useful in what you are doing. For example, on the homework, you'll be asked about like pricing as an example, and if I'm saying that I price in some like additive way, if the price is like additively close to the optimal price, pricing like a slightly above optimal versus like I'm slightly below does not have the same impact on your revenue, and so like sometimes you don't necessarily want to guarantee with this form. Okay, so this gives us the like exponential mechanism. Okay, which is for arbitrary queries. Yeah. Okay, let's say it like this. Okay. So we want to still do something of this form. We can't just compute the true answer. If I'm like, who wants to go to the beach or the Medina? I can't do like beach plus 0.2. Like this is not a meaningful thing. So the question is, how do we transform these sort of non-real valued things into things we can do math over? And the answer is that we are gonna do like a biased sampling with like an exponential bias towards things that are good. And we have to quantify what is good here. So we're going to have a score function. That is Q because of like a quality. It's a quality of an output. Okay. So my quality function is going to map from pairs of my database cross possible outputs into real values, where Q of X and R is the quality of output R on database X. Okay, so it might be if 99% of us vote for going to the Medina, then the quality score of the Medina should be higher than the quality score of the C. But if I had a different like a database with different votes, then it might be flipped. Also, if I am looking at prices, if I want to produce a price, well maybe prices that give me higher revenue given the bids or the values I have, those should have a higher score as well. So there's a little bit of art and magic in deciding what's the right quality score based on your application. There's no mathematical way of doing this, but it's just what is your objective. And in some cases, you have a really explicit objective. If it's I want to maximize revenue, then probably revenue should be your quality score. But if you're uncertain, if you're I kind of care about picking the best option, then you have to think about what is the good value here. A couple properties to keep in mind is a sort of better things should have higher scores. Okay, intuitively this makes sense. And you also want some sort of like smoothness of it, or you want to capture the idea of a close second. It's like if let's say that I give you the options. Do you want to go to the Medina, or to the sea, or to have an extra 2 hours of my privacy lecture? And let's say that 49% of people vote for the Medina, 50% go to the sea, and 1% votes for some more privacy lectures. Then we should have some way to capture both the Medina and the sea are pretty good options, and more privacy lectures is it's much worse. And so I don't just want to say C is the best and everything else is bad, because I want to capture, okay, there's some intermediate rankings as well. So with this, we can start to make things parallel to the a Laplace mechanism. So I can now define score sensitivity, which is going to be delta Q, defined in a very similar way as before. I'm going to take a max over all possible things in my output range, and a max over all x and xy that are neighbors, of the absolute value difference of my quality score on R under X, and my quality score under Y on R. So now if I ignore this first part, this looks exactly like what I have on F, as I'm saying, what is the absolute value difference of my function evaluated on X and Y? But I'm now taking a maximum value also over all possible outputs, because I have this sort of additional input here. And now note, I don't really have to think about neighboring outputs, because that isn't what we talk about here. I care about changing one person's data, but there isn't really a notion of sort of neighboring outputs, and so we don't have to mirror that. But I just want to say in the worst case over all outputs, because again, I care about having a for all, a quantifier over here. I want to make sure that I hide this amount. Okay, so the exponential mechanism is that we do a biased sampling with an exponential weight towards some things with a higher quality score. So it's my M, it's an exponential mechanism. It takes in X, Q, epsilon. And I'm going to output some R in my output range with probability proportional to exp of epsilon Q of X R over 2 delta Q. Okay, so we're seeing something, even though we're doing a different type of object here, we're sort of seeing the same thing arising here, how I have some delta F over epsilon, here it's a delta Q over epsilon. Also notice the same sort of term here of sort of an exponential of my thing that I care about, of my answer with this ratio, and we once again have it here. And
here, more Q is big, more I select because Q measures the quality.
Mm-hmm.
So
Yeah.
I want to select better scores.
Yes. Yeah, exactly. And so you have this like an exponential weighted bias towards things with a higher quality score.
Kind of Gibbs distribution.
Yeah. Yeah. Let's see, there's a normalizing constant here that is hidden. And again, if you want more privacy, then you're going to sort of like spread your weight out more, versus if you want less privacy, things are going to like concentrate more on things with higher quality.
Q, is there any axiomatic approach to select this function given a problem?
Basically, just these two things. In some cases, it's really obvious what your quality should be, and in some cases, it's not so obvious, and there's like many possible valid answers. And as long as you sort of have this,
It can be social welfare. It can be.
yeah. Let me tell you the privacy and accuracy theorems about it, and then we'll do a couple examples of this. Okay. So the theorem is first that the exponential mechanism is also epsilon 0 dp. I won't prove it, but this is one of the homework problems as well. I'll say it follows very closely to the Laplace version, except there's one trick that is kind of hard. And if you get the trick, then it's really easy. But if you don't, it's hard. But it in structure is very similar to that. Yeah, exactly. It's like that's what makes it tricky. Yeah. And in terms of accuracy, we have. Let me see which version of this I'll give. Okay. For all beta in 0, 1, we have the probability that the equality of the thing. Let me see. Okay, let R be the output of the mechanism. The quality of the thing that I output is going to be like a not much worse than the best possible quality. So max over all other R prime in my output range of Q x R prime minus delta Q log size of my output range over beta all over epsilon. And this event will happen with probability at most beta. Okay. So we're saying if I compare the equality that I get from this mechanism with the best possible quality I could have gotten, this is like opt. I'm going to be worse only by a factor of this a delta Q, which again is a sort of inevitable factor, and this log term involving the size of my range and the beta. So a couple of things to note here. The first is that you actually do have to have the size of your output range here. And that's because you're going to output everything with some positive probability, and so you have to spread out the probability mass over the other stuff. And if there's a lot of other stuff, then you're going to have to spread out more the mass there. There are some various tricks involving things like a VC dimension and fancier machinery, but the standard version is this. One more thing to note is that we are not saying, as in the Laplace mechanism, we said the value that we output is going to be close in value space to the opt. Here we're saying your output is going to be close to opt in quality score space. So it's like even if these are like real numbers, they might be very far apart, but they're going to have like a very similar like quality score. And this is important if you're thinking about like pricing, where it may be my like second best price is something kind of far from the best price, and things in between are going to be bad. And so this says I won't input things in between, but I'll output this sort of other price that is like close to good. Any questions on that?
In your statement of differential privacy, you didn't give the division cosine delta, but there was nothing about accuracy like this. Is
Yeah.
there any consensual definition of what should be the accuracy?
Not particularly.
You give it for each mechanism.
Yeah.
So it means that if you want to publish an article, you should give it.
Yeah.
And then debate about it.
Yeah.
But is there any general good rules? It's last deviation, I guess.
Yeah, there are some for these sort of standard problems of like SQ learning and PAC learning. There's some known upper and lower bounds that at this point are sort of like asymptotically tight, and maybe you can improve those bounds in some cases. But that's for the for the most sort of common cases. For example, if you're doing regression as well, it's like kind of known. But if you're doing a new problem, there's really nothing to compare against, except perhaps for the non-private version. And so like oftentimes you compare against that if it's a new problem that you are doing privately for the first time, and it'll say how much worse is the private version. And we know there's going to be some loss, and the loss should usually it's 1 over epsilon term appears, but again, it depends on the problem. And in fact, in most of the privacy research papers, the privacy proofs are kind of easy. As we saw in the a Laplace mechanism, it was a few lines. And the hard work is in this part, is in as I push through the fact that I added noise in a complicated algorithm where there were lots of things going on. How did that affect accuracy? And can I say it's good in some way?
Has being close second defined also in terms of substitute?
Nope, just in terms of whatever is your objective. What are you actually doing? What's your goal in your query? Because oftentimes you will have some function f, and it's what is your goal? What is your accuracy metric? If you don't just want high probability additive accuracy, but you want some other metric, then you can use that. In fact, let's do an example. Let's do a simple example.
Yes, about the exponential mechanism epsilon 0 dp.
Yeah.
The data in this case is just the n power x, or it's also the r?
It's just here. So you have how
the noise we add depends on r and q. It's still we only care about the data in the.
Yeah. So this is a public information. In fact, let's do an example that sort of goes through all these parts. I think that'll be helpful. Okay. So let's say I want to figure out what's the most common eye color. And I have collected a bunch of samples. So we'll call this F. Okay, so here the F goes from my database space to some R. Okay, so example is I want to learn the most common eye color. Okay, so this is my F. Okay, so I'll say, what's my data universe? Yeah, it's a bunch of colors, brown, blue, etc. Okay. And what's my single database? Yeah, it's like a database containing a bunch of colors. It's like how many people have brown eyes, how many people have blue eyes, etc. for all the colors. Okay, so this is my data. And my function, f, what's my function? Huh? Yeah, let's say it's the argmax of all the xi's. Okay. Okay. So this is our data setup. Now we can start thinking about applying this. So, yeah. Okay. So first, what's my output range? What should this mechanism produce? Yeah, colors. Okay, so that's my same. It's brown, blue, etc. Okay. In this case, it happens to be exactly the same as my data space. Doesn't have to be in general, but in this case, it is. Okay, so now what's a reasonable quality score? And I'll tell you, there's no obvious correct answer. So in case you are worried, there's no obvious correct answer, but the function should satisfy these properties. Yeah.
Maybe the color line is the frequency of the data?
Yeah. So let's. Yeah. So maybe it should just be how many people in my database have that color I, or I guess X, R. Huh?
Maximum XI.
So that's
XR,
our
not
goal.
XR.
Yeah. And it could be 2XR plus 5. It doesn't really matter. Any of these are fine, but let's say that it's simple because I just want something. So in fact, let's check. Better things are gonna have higher scores, yes, because if you have more count, then you're closer to an argmax, so it's good. And there's a sort of capturing sort of an intermediate goodness, which we also have because if you have more values, then you have more. Good. Okay. What is delta Q here? And let's use the add remove definition. 1, yeah, exactly, because you can only have one eye color. Or if you can have mixed, then put that in the colors. So then let's just put this all together and say, how do I run the exponential mechanism here? Well, I specify these. And then I just do exactly this. Output some R and R with probability proportional to X EQ XR over 2 delta Q. Okay. So if you want to run the exponential mechanism, the trick is not actually running it. It is figuring out what are all the other relevant parameters so I can just plug in and then just do something specific. Which is kind of true for the Laplace mechanism as well, but you only really have to figure out what is my a delta F, and then I can just run things.
And somehow, if you come back to decision theory, instead of choosing the best option, you choose the best option using the logarithm or whatever, discrete choice. You randomize so people will not know exactly what is your best.
Exactly.
What is your best choice? What do you prefer? So you have a little bit what's your preference.
Yeah, exactly. Okay, I think I'm gonna state the properties, but I'm not gonna prove anything. I'm just gonna state them and then we'll have lunch. Oh yeah, break, okay. Sorry. I thought it was done already. Okay, so let me tell you three nice properties that we like about differential privacy. So the first one is what's called post-processing. Post-processing. Which basically says that like if I take the output of a DP algorithm and I do literally anything to it, it retains the same differential privacy guarantees. So let's M, the maps from data to some output range R, be epsilon delta dp, and let F, the maps from the output range of M into some other R prime, be just anything arbitrary. Then this composition of first of like applying F on the output of M that will take from the data space to this R prime is epsilon delta dp. Okay, this is very, very nice because it says you can't break my guarantees. You can be an adversary. You can do anything you want. You can use arbitrary computation time. You cannot reduce the privacy guarantee. And intuitively, it's because you're adding entropy in some places and you can't undo that. Importantly, this F does not access the data. Again, it's just I see what you publish and then I try to guess things. We also have group privacy. Because this is stated for one person's data, for your data. But what if, for example, there are multiple people in the database who share your data? So if we're talking about a family that has the same address and shares the same data, what if you're in my database multiple times? So if we're talking about hospital visits and you visited the hospital 3 times, does this break everything? The answer is no, which is nice. So let M be epsilon delta dp. Then M is k epsilon k e to the k minus 1 epsilon delta dp for groups of size k. Things are a lot prettier if you don't have a delta, for example, as in the a Laplace and the exponential is then just k times epsilon. And so for a group of size k, you get a linear loss in your privacy, which again, if you're thinking about families sharing a home, okay, so k is 2 or 5 or 10 or but it's not a million. And so if your epsilon is something small, maybe 2 times that is okay, maybe 10 times that is less okay. It depends on sort of how small is the epsilon in the first place. But because differential privacy is about learning from the individual, from the population, and not from the individual, if your k is size n over 2, you're no longer individuals, you're the population, and then we can learn about you. And so if I put a factor n over 2 here, I'm going to get a really, really weak privacy guarantee, which is the goal. Yeah. Okay, one more. Composition. Yeah.
So if
Mm-hmm.
Does the other stand as well?
Not necessarily. Yeah. It's hard to imagine a thing that does this but doesn't do that, but maybe you can make up a pathological example where it's possible. I think that's an interesting open question. In fact, if you could prove that it doesn't, then give an example. That would be a interesting research question. Yeah. Okay. One more theorem, which is composition. And this is possibly the best one of all, because it says we can run multiple DP computations on our data, compose them in some way, and still have a DP guarantee. Okay. So let's Mi be epsilon I delta I dp for I from 1 up to k. Then the composition M, which is M1 up to mk, is sum of the epsilon i's, comma, sum of the delta i's, dp. So this tells us something actually pretty incredible, which is that if I want to go do something here, I know it's small, I'm sorry. It basically says you can add up epsilons and deltas, and it will work.
When you say composition, is M1 composed wrong?
Yeah.
No, it's not composition. It's the tuple.
Yeah.
So
Yeah.
You run them separately, you make a vector.
it's a vector.
Yeah.
Not the same.
Yeah. And so this says in fact, if I want to run some complicated algorithm where maybe I'm doing gradient descent and I want to do that at differential privately, I don't have to think about from scratch how do I do a gradient descent differential privately, but I can think about how do I access my data? Well, I do a bunch of gradient updates. Maybe I can add some Gaussian noise every time I do a gradient update, count up how many times do I do it, have some post-processing on those outputs, and then I'm done, and that's what my privacy analysis is. There's a fancier version of this that I have in the notes. In fact, this version is not the most tight one, but it's the a nicest to write down. But in the notes, there's a more advanced version. I think let's stop here. I magically got through everything I wanted to say, and we'll talk after the coffee break about how this ties into economics. Okay, welcome back. Do I just start? Okay, welcome back. We are now going to finally tell you how this relates to game theory and the kind of things we have been talking about all week. So you're now approximately differential privacy experts. One thing I do want to mention is that in my course notes, I link to a page where I have more course notes about differential privacy. These are what we did in part one is an abridged version of the first two lectures of a privacy course I give, and I have on the website lecture notes on more topics if you want to learn more. Okay, part two, how does this relate to game theory? Okay, so first thing is, and in fact I love it was made a comment in the break of well, this sort of already matches things we're talking about of changing one person's input is a Nash equilibrium and you keep everything else fixed, and we're totally going there. But first we have to think about how do I incorporate this like notion of like types and values and actions and all of this into like a differential privacy that's about like databases and functions. And it was observed. So yeah, so we'll say first in a like a philosophical way that is like a little bit of a roadmap. Like there seems to be a tie into like truthfulness, because in like Nash equilibrium, if you lie and if like everyone else is playing like a Nash equilibrium, you are doing worse, and so you might as well be like truthful. If you translate this into privacy land, if we can somehow like port over this like a Nash equilibrium concept, if you lie or if you don't purport in a DP algorithm, we're still going to get out approximately the same output, and so you like might as well be untruthful. And so there's something like fundamentally underlying in both of these, and this is the like a tie that we're going to explore. And this was a sort of like a line of work that we're going to explore. There was sort of like maybe we can use differential privacy as a tool to achieve truthfulness in games. If we can enforce differential privacy, maybe it will get a like truth telling as a Nash equilibrium. And so it was noticed that effectively you can rewrite differential privacy in terms of like a utility in games. And I'm now going to switch into like a game theory notation and start like talking about like types and utilities. Okay. So this is sort of like alternative DP. Is I can say a mechanism, and perhaps here it's nice that we're like calling our like a DP things mechanisms, because it's very suggestive of what's coming. M, the maps from a vector of types into some output is epsilon dp. So notice no more delta. If for all pairs of neighboring types, neighboring type vectors, T and T prime, by which I mean if I change like a one person's type report, and for all utility functions, over the output, the map from the range of my outputs into real values, they have to be non-negative. I have the following. The expected utility, if I were to sample R according to the mechanism run on T, my expected utility under U should be close to e to the epsilon of the expected utility if I were to sample R from the mechanism run on T prime of my expected utility. Okay, and so now we're sort of like mapping things onto the same language. It looks very similar. We're still talking about like neighboring databases. We still have a quantifier for all pairs of things that are the same except for your report. We've changed a couple important details. The most a dramatic one is instead of saying for all possible pairs of outputs, it's for all possible utility functions, and we're no longer talking about our probabilities. We're I'm talking about expectations. You can see this at a kind of intuitive way because we're saying, well, I know the probability that I output a certain R under these two neighboring things should be similar under DP. And so if I take expectations of that, then it should be close. one thing I have on the homework, oh yeah?
Is U here, like, it's like a vector of utilities for each person, or it's like one?
It's a single one. So let me call it UI. Yeah. 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 So you can think of this as being like, from a person deciding how to behave in a game. I can be truthful or I can lie. And I'm gonna keep fixed everybody else's report. And I can just change my report. Well, it's not gonna change my expected utility by much. Yeah.
Is there a particular structure to utility functions, or they can be anything?
So the only restrictions on this, and this is a thing in the homework, or in the problem set, is there's two things where this is not as fully general as the other definition. One is that you can't have a delta because you take expectations and things break, and this has to be a positive. So if you allow negative utilities, then things break as well. But aside from that, it can be anything. So one kind of immediate observation from this is that we're saying I can't really gain from lying. And importantly, this is regardless of everyone else's report, I can't benefit from lying. What do we call that? Yes. And what type? Yes. Approximate, and there's one more adjective. I wasn't here in the first two days, since I don't know if we actually do. What is it? Huh?
Well, I don't want to say.
Yeah. Exactly. I'm sure that MD know. So this is like a dominant strategy truthful, because it means no matter what the rest of the people do, this thing holds for me. But an important point is it is approximate truthful. Yeah.
But in some sense, it doesn't matter what I play either, right?
So you're one step ahead of me. I was going to do a bait and switch, and that is the switch. So yes. Okay, so we'll write the happy part first. So the happy part is that, and in the notes I have all the appropriate citations for these things. Okay, so if M is epsilon dp for, and we have a little bit of a caveat, so we have to have epsilon less than 1, because we're gonna turn this into a 1 plus epsilon and a Taylor expansion. Then M has 2 epsilon dominant strategy incentive compatible. So we love this in our games. And you might think, if you hadn't already known, you might think, this is amazing. How do I get a truthfulness in my games? I just compute something at differential privately, have it be truthful. It's amazing. And this is a very strong truthfulness notion too, because you don't even have to think about what is everyone else doing. But you're right in that this does not solve our problems, because
When you say positive, they should not be bounded or something. You can multiply by the boundary.
Yeah.
Because it's multiplicative, that's right.
Yes. Yeah. So this doesn't fully solve our problems because in fact, literally everything is at 2 epsilon dominant strategy incentive compatible. Okay, so sad face lying is also 2 epsilon DSIC. Okay, so our problems are not solved. There was a method that would sort of address this by tying together a DP mechanism with some sort of external enforcement. It's called the a punishing mechanism, where they would say, it's I'm gonna build a hospital, and I don't know where everyone lives. Tell me where you live, and I will like privately compute the best place for a hospital. And you might lie because, of course, we know you can like, you know, lie like I'm having an improvement. But the catch is you can only go to the hospital that is like I'm closest to you. So if I'm building like 3 hospitals, and you lie, and you say that you're over here, but you actually live here, you have to go to this hospital. And like this is not so reasonable. Maybe in some things like school choice or something, I like have the ability to enforce it, but that's like but that's like only in some cities and under some conditions. So you can like sometimes pair this, where we're saying you don't gain from lying, but if you lie, something else external is going to hurt you, and then it makes like a truth-telling strictly incentive compatible. But in reality, it's it's not really clear if you can actually do this, and so this isn't a very satisfactory answer. So I will next tell you what does work, but first, any questions? Okay. Okay. So it does work. Yeah.
For the 2 epsilon.
Yeah.
Also the norm of u or something like that. No. Depends how you define epsilon.
Epsilon has to be less than 1, so you can take this into a Taylor expansion, 1 plus epsilon, and then yeah.
But then
Oh yeah, I think things are. Yeah, I think there may be some implicit assumption that it's bounded or something.
Epsilon, the norm of u times epsilon, 2 times the norm of u times.
Yeah, I think there's an implicit assumption that's not written down of like a bounded. Yeah.
Smaller than 1,
Yeah. Yeah. Let me tell you about a joint differential privacy and how we can actually achieve things like this in games without having to assume that we can force people to only go to certain hospitals. Okay, so this notion of joint differential privacy was really introduced to solve this problem. I'll try to remember to write bigger. Okay. Where really what goes wrong here is that yes, it is true that everything else doesn't depend very much on your data, which is good in terms of how do I build a hospital, shouldn't depend too much on your data. But your utility should depend on your data. And how do we separate these out? And so a joint differential privacy was defined for a case where we can partition this output of the mechanism into one thing for each person. Okay, so maybe it's utility for each person. Maybe for doing pricing, it's what is your bundle and what is your payment for each person. And so there's something that we all compute and we all know, prices. And there's some part of it that is really just for you, and that's your bundle or your payment. So this is JDP. So a mechanism M that maps from a data set of size n now into an n-dimensional output range is epsilon delta jointly differentially private. If the following holds, so I need now for all people, for all I, and for all pairs of I neighbors, which I'm going to say rather than a general neighbor that can differ in one person's data, I'm going to say they will differ in the ith person's data. And this is important because we have to reason about the ith person's portion of the output. So for all I neighbors, D and D prime, here I'll make this a scripty. And for all subsets of like the rest of the output except for person I's output, so this is S, which is a subset of R to the n minus 1. And so this is like everybody except for from person I, the following holds. So probability of M, I'm going to say, I'll say M D minus I, which is like the portion of the mechanism's output except for the ith person, is an S, should be at most e to the epsilon of the probability times the M run on D prime, except for the ith person's output, being in the set plus a delta. Okay, so it's very, very similar, hence the name. And so we're saying that if you change your data, if like you are person I and you change your data and you're like a type report and we keep like everything else fixed, then like for all possible things that like the rest of the players in the game receive, they're going to receive the same thing up to this like epsilon delta guarantee. Notice there is no requirement on your portion of the output. So if you change your input, your output can like change arbitrarily. What'd you say?
So my change of action or report impacts me but not the others.
Yeah. And so like a couple of examples to sort of have in mind. One is going to be like a pricing. So like, it's like if I change like my own values or my own bids, I should certainly receive a different bundle, but that shouldn't change like the other players' bundles by much. One more example is like routing games. So let's say we're doing sort of like routing over network, and I'm going to ask everybody where's your home and where's your work, and then I'm going to like route you, and I'm going to think about like congestion minimization along the way. If you tell me a different address that you're going to, I should give you a different route, but that shouldn't change like the routes of the other people very, very much, especially as we're talking about like large games. Make sense? Okay, so we are very happy that we have this, and this sort of like captures what we want. But the question is, how do we actually achieve it? Because I just spent the last hour and a half telling you like all these algorithms about differential privacy, and now I'm like, nope, a new definition. And the good news is what's called the like a billboard lemma, which I'm not going to write formally because it actually is kind of like notationally intense, but I'll give you the idea because like the idea is very simple, and like check the notes. Okay, so this is what's called the like a billboard lemma. And the idea is that if I billboard, Blackwell. Where the idea is that if I compute something differentially privately and I publish it on a billboard, and then you all see it, and you can know your like a personal portion of the output, then that whole process is going to be JDP. So I will write it in words, and then I'll draw you a picture. Okay. So and like in the notes it's in math, but if you like the concept is so straightforward and the math is very like cumbersome, that it isn't aligned. Okay, so if you compute, let's say m of d in some epsilon dp way and publish it, and then like each person I sees m of d, knows their type, knows their like a portion of the input di, and computes their portion of the output, let's say like m d of I, as some arbitrary function of this dp thing, and they're like a personal part of the data, then this is epsilon delta JDP. Okay, I'm going to give you a picture, and then we'll do examples. So let's say person I has their like D1 up to Dn, and they report this into some m that is like an epsilon delta dp. And this then like publishes m of d. Okay, and so like this is my billboard, and so it's like public, everybody sees it, and this then like goes back to each person, back to like person 1 up to person n, and then this person can know what is my f1 of this output, m of d1 dot 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 up to fn of m d sub n comma dn. So I can draw a box around this, and I can say in that case this whole thing is some m prime, which is epsilon delta JDP. So the way that I achieve JDP is I first compute something differentially private. I tell everyone, and then you see like your. I think the line actually goes here. You see that, and you know you're like a private information, and then you can like figure out what should you do. Yeah.
I'm a little bit confused about the purpose of the billboard. Why can't why do you just show it on a billboard and everyone computes their own? Why can't the mechanism compute it for you since it already knows the D?
Because he doesn't know the real D.
So that's excellent. This is where I was going. I drew this in a very sort of like suggestive way in case this sparks other things you might have seen that look like this. I don't know if it was like I talked about on Monday or Tuesday, where like people like truthfully report, and the mechanism does some stuff for them, and then tells them here is your sort of like optimal thing. Was this like I mentioned on Monday and Tuesday? I don't know. Yeah. Yeah.
So repeat. So you have D1, Dn. Each one knows his type. Say D1, Dn. Report to the mechanism. Mechanism do some computation.
Mm-hmm.
So there is some output.
Yeah.
Output is a vector or is one
It's like a one thing for
It's
each.
one recommendation
for each person, yeah.
This recommendation is revealed to everybody or just to each person?
Just to you.
Okay.
So does this ring any bells?
Okay.
Revelation principle? Was it mentioned? Yes? Okay. Okay, good. Yeah. Yeah. So this is something like that, where instead of saying like, tell me your true type, and I will optimally deviate on your behalf, and I will tell you what is the result of that optimal deviation. Instead, we're saying like, tell me your true data. I will do something privately, and I will tell you what is your like optimal strategy or your like optimal output. Yeah.
Should I think of this as incentivizing collaboration? Like everybody's life is going to improve if they know MD, but they don't want to reveal their DI. So
yeah.
Then MD is revealed. So they.
Let me say a couple more things, and then I'll come back to that.
My question is whether do you reveal MD1 to player 1 MDN, or there is one MD for everybody?
I see.
Yeah. So let me give a couple examples of this. So in our pricing game, let's say that like I want to compute revenue maximizing prices in a market, and I have like lots of items and lots of copies. And so everyone is going to tell me, how much do you value each item? I'm going to privately compute revenue maximizing prices. I'm going to publish them. For example, at a store, I'm going to say like, here's our prices. And you can just know like, how much do you value each item and the prices, and then you can like compute what is your optimal bundle, what is your payment. In the like a congestion pricing, in the like routing game, minimizing congestion, everyone can tell me where are you going from and to. And if I know some like public knowledge about like congestion of like this freeway has 3 lanes and that one has like a lot of stoplights, I can like compute what is the optimal like an equilibrium traffic flow, and I can then just like tell you how bad is traffic going to be on each road. For example, as like Google Maps does, is it says like this one is red, this one is green, and then you can decide for yourself how to drive from your source to your sink.
So can I ask a question? So at the end, condition tells that once you know your type and the public information, you cannot infer, at least with the high probability, you cannot infer other players' types.
Yeah, 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 yeah. And like, yeah, and like one more example that will like address your question that I don't actually talk about in this, or I won't because I want to like end on time. Is you can do this in a more general case. Is you can say like if I want to like compute equilibrium of some game, I can like have everyone tell me their types. I can like compute like a Nash equilibrium of the complete information game, and I can just like tell people how they should behave in equilibrium of this game, and this will, assuming everyone is like truthful, this like will form a Nash equilibrium of the game. And there's a couple details here or here. Here's a color. So there's a couple things that might go wrong in this. So if you are truthful, and if I tell you you should play up and this other person should play down, and you do that, then we are good. But you don't necessarily have to. And this is how this differs from the like a punishing mechanism where it's like you can only go to one hospital, which would be the equivalent here of saying like as you type into Google Maps what's your address, the car automatically locks itself and just go, and you can't do anything else. We might be there in the future, but we are not now. But there's a couple things that might happen. Is this might be a lie, and you might like a deviate over here. So you might say, well, like, you know, I'm gonna lie and say that I'm going in this place so that then it won't route other people there, and then when it comes time, I'm gonna do something different altogether. So now, like, you know, to your question, how does this help? Is that, like, if we didn't have this, let's say we're like in a Bayesian setting, I can only have a like a Bayes-Nash equilibrium given people's beliefs. But if I know their types, and I can, like, you know, compute like a Nash equilibrium of the, like, complete information game, if I have everyone's type, then I'm, like, you know, doing something better. I can improve. I can, like, have a better equilibrium. But the challenge is, like, these parts. And so, in fact, this is where sort of like a differential privacy and, like, these like types of guarantees come in. And, like, here's where I'm going to be hand wavy, and there's, like, you know, a lot of papers on this, and I will not go into very much detail. Like, effectively, because this is DP, you know that if you lie, this thing is going to compute like approximately the same equilibrium if you lie versus if you are truthful. And so you can't really change what is computed here. And so you know, like, the game is going to report to everyone what they should be doing in a Nash equilibrium. And so if other players are playing in like a Nash equilibrium, you should do what you're told here, and you can't gain from, like, I'm deviating. And so this allows both to have a, like, you know, complete information Nash equilibrium rather than a, like, a Bayes Nash, but it also allows like an equilibrium selection in the, like, complete information game. So if there exists like a multiple equilibria here, if you are truthful, which you should be, this thing can then pick, like, at the best equilibrium and can tell everyone to play that. And because everyone else is going to be playing the, like, a best equilibrium, you should too. Yeah.
So for the example of the voting game, so even if we assume that everyone is truthful,
yeah,
and then so I get, like, the state of the network and an output, and I can see who goes where, like, I might be incentivized to deviate in some sense, right? But if I do this and others do this as well, I'm not deviating on the same data set. I mean, I'm also going to change, so it's not exactly M1D that I'm playing against, but it's also like a modified version of everyone's terms, right?
Yeah, yeah. So this does not prevent against, like, a large scale collusions. And so getting into, like, you know, group privacy, if you have like a small group who wants to, like, deviate, they can't gain because, like, you know, group privacy gives us group strategy proofness for a small group. If it's a large group, then sort of anything can, like, happen. But if you have a large group that wants to, like, deviate, why are you, like, even, like, you know, using a mediator if you already have a plan?
So then I have a very follow-up question. So can I think about this in terms of correlated equilibrium, for instance? Or
Yes. Yeah. Exactly. Yeah. So actually, one point here is that I am, in this part of the lecture, I'm not really talking about privacy for the sake of privacy. You can, and certainly there are games where sort of, like, you know, privacy is important and you might, like, you know, worry about privacy. But in this case, I'm not saying that I want privacy. I'm saying that I want truthfulness. I want this, but I have a sad face. And so, like, you know, how can I sort of, like, change things to use, like, a differential privacy as a tool that will give me truthfulness in games, but it just, like, requires some sort of like accompanying machinery besides just doing this. Yeah.
So, but like, I agree that telling the truth and then following the recommendation is an approximate best response, but so is lying and then computing by myself I guess it's more work, but.
Yeah. So it's an approximate best response.
But there are like approximate best response that involve me lying, right?
Yeah. But this is only sort of like a Nash equilibrium style, because if we're saying as long as like everybody else is truthful, then we genuinely are going to like compute the Nash equilibrium of the game. And if everybody else does what they're told, then it's like everybody else is going to be playing a Nash equilibrium, and so therefore I should be too.
But then there's another Nash equilibrium where everybody else is doing the truthful thing and I'm lying and computing my best response.
But that wouldn't be an equilibrium because your lie is not going to change this equilibrium, and so like they're all going to be playing like at the same equilibrium they were, even if you hadn't lied.
Then I can compute what I should be doing.
But it's like if they're playing an equilibrium, then like you should do the same equilibrium strategy. So there's sort of like a game and a meta game here, and there's the sort of like complete information game. And so I'm saying what this tells you is it tells you here is your part of a Nash equilibrium in the like complete information game. And so if like everybody else is going to be like playing like this like a Nash equilibrium, then you can't benefit if you deviate. And you can't like make them move to a different equilibrium.
Is I'm forcing other people to also do their thing because it's a best response to what I'm doing. But because of this differentially private thing, if I remove my data, like if I just don't tell Google Maps where I'm going, it's still going to give the same traffic information, so everybody else's behavior doesn't change.
Yeah.
And
so they're still playing a Nash equilibrium.
And so it's fine for me too.
You should also play your part of a Nash equilibrium.
I could, but I could also not tell the.
Yeah, but if you deviate from a Nash equilibrium, then you can't improve utility.
Yeah, so it's weak.
Yeah.
And I mean, that was the complaint.
Up to the.
But the reason I'm pushing on it is that was your complaint for the first proposition.
No, it's actually much No, it's actually much stronger. So it's like think about the pricing approach. So let's say that I publish prices. So we could equivalently tell you Nicole, you should buy 3 apples and 1 orange. Or I can say Nicole, here's the prices of the apples and oranges, and you can decide what to buy. And this should tell you I'm given your type, what are the right number of apples and oranges. But if you lie about your if you lie about your type, you won't change the prices. And given prices, I'm going to tell you what is the best thing to do. And so
the wrong bundle, but I could just not buy that bundle and buy what I want.
Yeah.
I think if you lie, it's not going to affect that much, but it's going to affect a little bit so that the payoff is strictly greater. Have you told
Yeah. So I think the difference, Nicole. So it's actually much stronger, because imagine if I didn't tell you what the prices were, and you had lied, and you actually love apples, but you lied and said you love oranges. Then I'll tell you buy lots of oranges, but I won't tell you what is the price of apples. And so you might deviate and buy lots of apples, but it might be that apples were very expensive, and so even doing this is a suboptimal thing for you. I'm gonna.
Yeah, I think we should.
Yeah. Yes. I'm gonna move on. Yes. Do I want to say anything else here? But it does address this sad face, and in fact, you can lose if you lie, with the caveat that it's approximate up to some things that depend on epsilon. This in general only holds for certain games that are what's called large, meaning the sort of each person's action has a small effect on the other people's outcome. So for example, you can't do this in a single item auction because then it's supposed to be one person's bid affects everybody else's outcome. But you can do this in a game where there's thousands of apples and you want apples. Okay, so this is sort of up to here is we have explored this part, and we know how to achieve a truthfulness in games using DP, additionally under some parameters and some assumptions. I now want to switch gears a little bit and talk about markets for data. They were promised at the end of Bo's talk. So we have now talked about quantifying privacy. We have talked a little bit about utilities, and we have an object, and there's I can measure it, I can value it. Can I buy it and sell it? And markets for data that I'm a little bit gonna call markets for privacy, because let me first actually motivate it. Okay. So let's say there's an analyst. Analyst wants to compute something, some f of x, but they don't have the data x. Okay, and so they're doing market research. They want to know who likes what. Only you know what you like, and they have to ask this. So you could offer a payment. So let's say they will offer payment PI to a person I for their data XI. And now we don't even have to mention privacy because we have a market. I want to buy something from you. But the question is, maybe some things would be very expensive to buy, right? It's imagine if I say, give me your medical record, I'll give you $5. You would probably say, no, that's a terrible idea. But maybe if I say I'm going to do some differential private analysis on your data, and here are some guarantees, here's my epsilon, you will be protected in these ways. Can I have your data? I will pay you $5. Maybe that no becomes a yes. So another benefit of having privacy is that you can oftentimes get data for cheaper, with the caveat that as we saw before the break, there's some loss in accuracy, but maybe the sort of loss in accuracy is better than the additional cost, or you can get more data for the same budget, and that will give you accuracy improvements overall. So we're going to model this as a utility function, and let's just assume each player I has utility function. We're going to assume quasi-linear utilities. Where a person I is going to have utility, which is their payment. If I pay you PI dollars minus some, we shouldn't use F. I'll call this H. Minus some F that depends on the epsilon, but it also probably depends on something personal about them. And some people are just really worried about their privacy and don't like sharing data. Some people don't care. Some people think that sharing data is valuable if it's for a good purpose. Maybe this costs, it depends on your data. So I ask, do you have an embarrassing disease? If the answer is yes, you might require higher compensation. So there's a lot of things that go kind of go into this. Actually, okay, yeah.
There's a new variable CI.
Yeah.
I think wasn't defined.
Yeah.
And this is utility for what?
Kind of CI, no? Not CI?
For some personal cost parameter CI.
But for what?
Quasi-linear utility for sharing data with some epsilon dp computation. Okay.
So CI depend on epsilon?
So
It's independent on epsilon? Because it's as if I is a function of CI and epsilon, but CI also is a function of epsilon?
So in fact, you're sort of like going where I'm going next, which is like, what on earth should this function look like? Because I can say, well, you get a gain from your payment. We know how to reason about that. And then you experience some cost for sharing your data. And now it's very likely this it depends on the privacy guarantee you are getting. But it might depend on some other things. And so it's like, well, my data is like, I have to transcribe it, and that's costly to me, and so I put it in here. It might be like, oh, I don't trust you, so I have a high cost, and you better pay me a whole lot if you want my data.
Just to be clear, if I don't share data,
then it's zero.
Epsilon equals to 0 in this.
Yeah, I'm like being vague on purpose because this is a part of the question.
Are you going to give us open programs?
Yes.
Oh, okay.
Yes, exactly. In fact, this from here to the end, is like mostly an open problem. I'm telling you what's known, but I'm also warning you in advance it will be unsatisfactory, and that means there are lots of interesting research questions. So let me tell you.
So
Yeah.
I assume, for example, FI CI of 0 is equal to 0? Is that like a good?
Sometimes. So actually, let me give you an example. Let's say that I stop you on the street, and you're with a bunch of friends. It's like you, it's Nicole, it's Abdella, it's Rita, and I'm like, hey guys, I'm doing a study. I want to know what fraction of the population has an embarrassing disease, and I'll give you $1 if you tell me. And they're all like, yeah, totally, yeah, totally, yeah, totally. And you're like, you have the embarrassing disease, and you're like, oh, that's not a good deal for me. I don't want to admit this in front of my friends. Sometimes being asked the question reveals something about your data if there is a correlation. So that's a part of how should this function look and what should it include?
But cost is private.
So then you want a variable for that. Or where you ask the question should be a variable in the form.
Yeah.
But it's apparently not.
So I'm going to tell you lots of possible forms of this. Some of them will include additional variables. This is a placeholder. Okay, so let me sort of I'll walk you through historically what has been proposed and why we're maybe not completely happy with it. Okay, so first you said, okay, well, so we know that this can be approximated as a 1 plus epsilon times my expected utility. So maybe if my utilities are bounded, something like this, maybe I should have some additional. So this can be. So this is what I would have before. And then I have some like, additional epsilon loss times like, let's say that my like, utilities are bounded by 1. So then this is a like, negative term. Maybe there's some like, other constant here if my like, utilities aren't bounded by 1 or something. And so it's like, epsilon times a constant. So maybe we should say that this like, Fi Ci epsilon should be some constant like times an epsilon. And then if I want to like, plug this in and like, solve for a like, market equilibrium, market price, well, I can like assume costs are generated uniform 0, 1, and then proceed. Okay, this is nice because for one thing, it's a like well-behaved function. I can like unplug it in and we're done. But there's a problem, which is that like this is a bound, and I'm pretending like this is an equality. So maybe I shouldn't have this as an exact equality. Maybe I should say, okay, so it's actually like upper bounded by this. Because like, that's a worst case bound, and so I can say it should be at most my bound. Okay, this makes sense. But the problem is, if I want to like, apply all my like market design techniques, I can't just have an upper bound. I need a function. I have to like, plug it in and solve. So like, what do we do with that? So then it was proposed, maybe it should be based on like, how much information leakage is really happening. So I said maybe we should have some notion of like a mutual information here. So maybe it should be the mutual information between your type and the like an output of the mechanism of your strategy on your type and keep fixed everyone else's. Okay, and this is like, pretty well like motivated because we're really saying where your privacy loss should somehow capture how much information is leaking about you. Okay, and so this is a player's strategy. Yeah.
If truth or not is not the best strategy, this is my optimal strategy.
Yeah. And in fact, originally it was just like, your type. But then it was pointed out, actually there's like kind of a paradox from the fact that it like a depends strategy. So it's like kind of weird that it depends on your strategy here. So like, here's an example of a game. Let's say I'm like building a sandwich, and I want to know what's your favorite type of bread. Okay, do you want rye bread or do you want whole wheat bread? And imagine this is like very secret. Okay, and let's say like my prior is that you are like uniform, is it's like half-half. So there's a like strategy which is being like a truthful, where the like a probability here, I'll do this. Is he like probability that I observe rye is a half, and the probability that I observe whole wheat is a half from the like observer's output. But imagine if you just like randomly said each with like a probability half. So again, the like probability I will observe rye is half, and the probability I observe whole wheat is half. And so there's like something weird going on if we're talking about like how much information is leaking about your type by the output of the mechanism. it's like, well, it's weird that like in both cases, I'm going to observe the same, like a distribution over outputs, where in one case, you are telling me exactly your data, and in one case, it's like totally random, and these two are exactly the same to me. So it's a little weird to be talking about like, how much does the output of the mechanism leak about your type when there's like, something in your head that like, can't be observed.
Are you using condition on the type on purpose? Your probabilities.
So these are these sort of like observer Cs. And so the observer who is like computing this mutual information.
Again, you didn't condition the probabilities on the type.
Correct. Yeah. Yeah.
And so it could be, in the truthful case, my type is just 50-50 something else. And then it's R or W based on my type. Exactly.
Right, right. But importantly...
If I also enter randomly, my type is random, but also I could enter randomly. And then it's also going to be R or W.
Yeah.
50-50 chance.
Yeah. And like that's what we're seeing is sort of weird here. It's like this is trying to capture, I observe Rye, and I like try to learn things about your type. But it really matters, were you playing this strategy or a different one? And like the observer who's trying to make inferences like can't tell these apart, and these are very different in terms of how much information they're leaking. And so like somehow this is not really capturing what, like this is not really capturing information leakage in the way that we thought it was.
The observer cannot compute the cost, only the person that they know what they are doing, they can compute their cost.
Yeah. Yeah, and so like this is why it's a paradox. It's like, okay, this is not what we want it to be. So then there were other approaches that said like, maybe it should be outcome dependent. So there should be some outcome dependent loss function. Or here, I'll use cost. So I don't think of like a machine learning cost function. Where it's like, maybe I'm gonna like, announce some like label of like, yes, I think you have a disease. And if I say that, that's like much more embarrassing than if I say you don't. And like, even though those are both random, maybe like, one of them reveals more information. Or like, or like in a dramatic way, imagine with like probability half, I'm gonna use the Laplace mechanism and compute the mean. And with probability half, I'm gonna like report null. Well, if I say null, you have received no privacy loss whatsoever, and so somehow that should be incorporated in here. Okay, so then we said, there should be some G, like it depends on the mechanism and the output that is observed and on your data and on the rest of people's data. And that should be bounded by some like, CI times like, something like a leveraging, something epsilon like. I'll like, say it's epsilon, but well, okay, no. Actually, I guess here. It's a weird function, and it like isn't like a particularly interesting, but I will put it down just to be explicit. Okay. Max of di prime and di double prime. Of this ratio, if I were to run on your data and keep everyone else's fixed. Here. Versus if I use di double prime and keep everyone else's information fixed. So I'm sort of capturing like something that is epsilon like, but I'm only restricting to a specific output. And so I'm saying like given we observe this output, what is your like a privacy loss given that? Okay, and then and then your like privacy cost fi of ci epsilon is just your like expectation of your gi m r di d minus I of the other players when we sample this R from M of D. Okay. So I'm saying this is your sort of like expected privacy loss, whereas like this one is your worst case. This is your like upper bound, and this is your expected privacy loss. Yeah.
So I mean, maybe it's related to like the illness example you said before, but now the cost is correlated with your income, right? With your own private data. So if you are the only one to observe it, if I post a price, for instance, and I know that if you have like the wrong type of data, you're not going to accept, this also gives me information on your type. So in some sense, if I ask you a question, you have to answer, otherwise, like you're going to disclose completely your type, and you would get it for free, right?
Yeah. So like I'm going to talk very soon about like how do you actually like formulate this like market, and that's also an open question. But like one of the questions that's important is sort of what does individual rationality look like, and like can you just like accost people on the street and they cannot prevent hearing your offer, in which case they like are going to satisfy a different type of individual rationality versus it's like, you arrive at my game, hear an offer, yeah. And then have to decide. I'm going to say a little bit more about that, but first let me conclude this.
Sorry, does this address that paradox that you previously raised, or?
No, it's sort of like going in a different direction of like, maybe this is not the right function, and instead we should have this function because it depends on sort of like things other people can observe, because it depends on the outcome rather than on your strategy. You can do a little bit of work and show that then using this, if I were to deviate, if I were to look at the benefit from I'm deviating here, okay, if I were to look at the comparison, should I, right up there, maybe you can't see, okay. If I were to look at the comparison, if I sample R according to M of D of this GI function, which is M R DI D minus I, minus, if you were to think about deviating, if you were to do something similar to this, of comparing these sort of additive difference with and without you. If I sample R according to M of DI prime and D minus I, so again, I'm keeping everyone else fixed and looking at this, DI and D minus I. If you do some analysis, you will see this is less than 4 times CI epsilon squared. Where did I think I'm missing this? Oh yeah, good. CI is there. Okay. So this is saying how much more information is revealed about you with your data versus without your data, or like if you lie versus if you are truthful. An expectation is gonna look like epsilon squared. So maybe we should say that our Fi of Ci epsilon looks like Ci epsilon squared. And there can be a 4 in there, or like some other constant. And perhaps this should sort of also be this. So unfortunately, this is where the story ends. And I promised you would not be particularly satisfied, is we have some reasonable mathematical justifications for thinking maybe this Ci should look like Ci epsilon, which is if you care about the worst case privacy loss. Maybe it should look like Ci epsilon squared if you care about the average case. But I think none of these are particularly compelling of being like, yes, obviously this is how we should think about modeling like a privacy loss for sharing data in a DP computation. So in fact, this is one of the questions in the afternoon problem set is can you think of something better? Is there something smarter? And is Jason said, maybe we need some extra parameters. Maybe it's weird that all of these don't include the data. Should it include xi as well? This seems important. How do we capture correlation? As I'll say shortly, there's also questions in the market setup, and so it matters how people hear the offer. As I was saying, it matters if I can harass you on the street and ask you to sell data versus if you come to my shop to sell data. All this matters, and this should somehow be incorporated into the utility function, and there's not really a clear answer.
Perhaps it depends on the application.
Yeah, exactly.
Because, for example, if you share some data, maybe you are sharing some technology that you are inventing, and someone will give a price, but he will have access to everybody's discoveries.
Yeah.
And they may do this. It has lots of value for him.
Yeah.
It depends on what you are doing,
I think a part of the challenge is that you're trying to write this for all possible markets. But really, it depends on what you're doing. And so it's maybe more fruitful even to say, I'm not trying to solve it in general, but in one application I have in my mind that I think is interesting, I'm going to write down the appropriate model for that particular market. And I think there's a lot of value for that, and a lot of need, and a lot of open questions. Yeah. Ooh, good question. That's also, it depends, and that can affect things. So there's work showing of how does it affect things if these are seen or not. So if they are private, then I can sort of tailor this. I can pay different people different amounts. Perhaps if you have data that's more valuable, I can pay you more. But if payments are public, then your payment shouldn't depend on the content of your data. You can think about this CI parameter. Is that public or private? Is it correlated with your data or not? Is it just, I'm asking you to do a survey, and some people like doing surveys and some don't, in which case it's a lot easier. But if this CI is I know that I have the embarrassing data type, and that affects my cost, then also that gets a lot harder too. I think there's just not really enough models exploring all of these and translating them into markets. Okay. I'm gonna posed with an even vaguer open problem. I go, you thought this was vague. Wait until you hear the next one, which is okay. So like, imagine that we could do this. Imagine that we're like, yes, I have the perfect utility function. I feel good about it. It's well motivated and it matches things I'm trying to like capture and practice, et cetera, et cetera. Now, how do we build a market for it? Okay, so we have like lots of optimization tools we can apply. So I can like start to write down. Maybe I want to like maximize accuracy, subject to, I have a budget constraint, and maybe I have some like individual rationality constraints. Maybe I have some IC constraints. Maybe I don't. And this is also a question of like, can people lie about their data? Or is it verifiable? Is it like, show me your like driver's license and take a blood test and I can verify? Or is it like, tell me what movie you like the most for the Oscars? So this can be both like the content of the data or your cost. Okay, and in some ideal world, okay, so we know how to like optimize stuff. I write down an objective and some constraints, and then I solve. In fact, I can like translate a few of these into math already. So my budget constraint, fortunately, that one is a well-behaved one. Let's say that I'm gonna like a trade-off, like I'm gonna have the sum of my payments has to be at most some like a budget constraint B. For the individual rationality constraint, I can also do this. Like I know that my payment minus my privacy cost should be at least 0. And again, depending on these like formulations, maybe this is what you want and you incorporate this sort of like asking into the cost function. Maybe your like individual rationality constraint looks a little bit different if you can like accost people on the street and they're going to experience negative utility and you can't like do anything about that. So like there's some non-trivial stuff here, and this IC constraint again, it's like data or cost. But we are not quite ready to just like solve an LP. Yeah, is there a question?
Yes, the viewer problem also makes sense, right? So minimize the payments with the constraint on the
Yeah. Totally. So let me do this. So we can like swap accuracy and budget. I can like minimize payments subject to a hard constraint on the accuracy. Both of these are fine. And it's important to remember that the accuracy depends on the epsilon as well. And what I'm really maximizing over is my epsilon and my payment scheme in this case. But there's some important details missing here. And this is my sort of like open problem is really a family of open problems. It's sort of how do you actually do this? Because writing it in this way hides a lot of important details. Okay, so the first one is sort of like market constraints. Or like market design questions. Of like do I like elicit these costs? In which case I have to have an IC constraint. Can I like verify the data? Or do I have to make sure like people are like truthful there? And I mean already this is like you can spend a month thinking about these, and that's only our first bullet point. There's a question of the accuracy metric. of what exactly are you trying to do here? And this is where thinking about a specific application, a specific market is really helpful, because I can plug in the Laplace accuracy guarantee and talk about high probability additive accuracy. Is that the right thing to be doing here? Do I have other metrics instead? There's a question of sort of incentivizing a participation. This should also go into my accuracy metric, and so this should include sort of goals and a participation, which is related to a question of should everyone participate? Okay, which this IR constraint sort of assumes that everyone is going to participate, then I have to satisfy this. But they may not, and in fact, maybe some people are going to have a really, really high privacy cost, and maybe I should exclude them. In which case, first of all, I should include that to my accuracy metric, is including of how many samples am I getting. But also in terms of computational stuff, that then turns this into an integer program if I have a binary variable of who is participating or not, and that is not so good. Or even if I take an argmax at 0, all of a sudden this is no longer an LP, and I can no longer solve it nicely. There's this question of FCI epsilon that we have talked a lot about over here. What's the right form of that? Probably this also depends on my setting and my accuracy notion. There's handling a different costs, or I'll say heterogeneous costs. Okay, which is more of a sort of algorithmic perspective in addition to this economic question, should everyone participate? But there's also if I have some people demand strong privacy and some people demand weak privacy, can I somehow give them different epsilons? Should I give them different payments? Well, it matters if the payments are public or not. And algorithmically, how do you give different people different epsilons in the same computation? And would it improve things? There's this question of handling correlation that I mentioned before, which sort of goes into the privacy cost, but it may also appear other places. For example, if people with type 0 tend to have lower costs than those of type 1, and I just try to minimize my budget, well then I'm going to get a biased sample because I'm going to buy samples from all the people with low costs, but this is not helping me in my accuracy. And finally, and this is a completely open problem that I thought about at one point and it was hard, and so if anybody solves it, tell me, or collaborate with me, which is how do you turn this into a two-sided market? Where instead of saying there's an analyst who's going to buy data from a bunch of people, maybe there's lots of companies who want lots of functions evaluated accurately, and there's lots of people who will provide data at a cost. How do you a market make in this, where maybe there's some intermediary who can receive payments from the people buying information and pay individuals who are providing information, and the goal is to sort of sort of like, maximize profits from that. And what makes this hard is you also have to like, maintain a differential privacy while like doing this entire thing. Huh? Yeah. So this is saying there's like a single person who wants to buy the like a value of a function. What if there are like many buyers and many sellers, and the intermediary gets to maximize over like epsilon and p and who to buy from and so on. We like have enough of the tools that it seems like it should be done, but things get kind of tricky. But I still believe that it's like a doable and it's possible. And then the final point is sort of like computational concerns. Okay, and so if this is a like linear program or a convex program, you can just like hit run on like Cplex, Gurobi, and you're done. But if you try to like formulate these in like even like mildly interesting ways, it becomes highly non-convex. Are there things you can do to like convexify it? Are there tricks? Are there assumptions you can make to actually make it solvable? And there have been papers that I was like honestly too lazy to like cite all of them here, but there have been papers handling a smattering of these problems. But I would say like 5 to like 10% of the space has been explored, and like most questions you would think of have not been solved, and there are like a ton of interesting questions in this space. So in fact, one of the afternoon problems is to like try and solve this, and it's an open problem, but I think it's one where like if you write down something interesting and you solve it, that like genuinely could be a paper that like would be appreciated. So that's all I have. Questions, yeah.
I mean, isn't this problem like maybe it is a two-stage structure because you can see the prices as the first stage variables and epsilon as the second stage. So I don't know if you use the compositional methods, maybe you can solve this more
For this?
I mean, in particular, if that and the data constraints are linear.
Yeah, that's the problem. Is they're not, or they're not if you write them down the first way. But sometimes with some like massaging and some other assumptions, you can make them be, and that's sort of a part of the question. Is like if you like first thing that you write down will not be, but maybe some other interesting variant that is equivalent and important, or like equivalent under some assumptions will be. Yeah.
Like, is your assumption already that we at the very least need like a trusted intermediary? It just seems like there's like a tension between the stuff that we looked at yesterday, like data Shapley and differential privacy. Like these things seem like fundamentally in contrast. If you're trying to set the price based on the marginal contribution of your data, but then it has to be differentially private, then this has to be within some epsilon, and so then you can't get any signal on that.
Yeah, that's a good point. Is we're not even like claiming to be fairness. I think that's a like additional constraint is like fairness. Are we like paying people equitably? Is we're only looking at like IC and IR. But I think that is a like very very well like motivated question. Is like can you also add some type of like equity constraint? Yeah, and that, as far as I know, has not been explored at all. Yeah.
Can I ask you two questions?
Yeah.
What do you mean by handling correlation? Is it related to social data?
So this is like handling correlation between the cost and the data, which like really sort of implicitly in this, even in this setting, it's like this is only useful to me if I assume something about the cost. Of like, okay, maybe my like CIs are sampled IID according to like a uniform 0-1. And I can assume that, and then I can like solve my optimization problems nicely. But like, what if people's privacy costs are not uniform 0-1? So one like common assumption that is used for this is we say, okay, let's say there's like your like, data universe can be 0, 1, and let's say that like, 1 is like at the more embarrassing type. I'm asking, do you like have a disease? And then I say, well, these costs are like distributed from some x sub xi, where maybe I say like f0 is like uniform 0, 1, and f1 is like uniform 1/2, 3/2, or like something like this for like this one, like first order stochastic dominate the other one, and so I think like this question is sort of like implicitly, what do you assume about the CIs? Because like you can only solve this if you know something about the like CIs, and if you don't know that, then you can't solve it. So you also have to make some assumptions here.
So this is the like two-dimensional mechanism design problem in which you don't know the type is both CI, the private type is both CI and X.
Yeah. And sort of like what you assume about CI will affect what should your IC constraint look like. If like should it like include CI? Should it not? Is CI important or not? Yeah.
Also, I wonder how this question is related to like social data, in which if someone has reviewed their privacy, maybe you can based on his information infer others' privacy.
Yeah, good. So this entirely assumes that sort of like everybody's data is independent. That like it would be important to explore, but then you have to like add some like additional things on top. Is there like underlying graph structure talking about who is connected? And sort of even in this simple case where like things are independent across individuals, we don't really know how to solve it. Yeah. All right, thank you. So enjoy like us solving these problems after lunch.